Welcome to this walkthrough of LeetCode problem number 2006, count number of pairs with absolute difference k. In this session, we'll explore the problem, analyze different approaches, and break down the solution step by step. Let's get started. In this problem, we are tasked with counting pairs of indices in an array nums that satisfy two specific conditions. First, the indices I and j must follow the rule 0 equals I less than j nums.length, meaning I comes before j in the array. Second, the absolute difference between the elements at these indices, nums I, nums j, must be equal to a given integer k. The absolute value, denoted by ex, ensures that we are only interested in the magnitude of the difference, not its sign. The input consists of an array nums with a length between 1 and 200, where each element is between 1 and 100, and an integer k between 0 and 99. The output is a single integer representing how many such pairs exist in the array. Let's explore some examples to understand this better. Consider the first example where nums equals 1, 2, 2, 1, and k equals 1. We need to find all pairs I, j, such that the absolute difference between nums I and nums j equals 1. The valid pairs are as follows: 0, 1, because a nums 0, nums 1 equals 1, 2 equals 1, 0, 2, because a nums 0, nums 2 equals 1, 2 equals 1, 1, 3, because a nums 1, nums 3 equals 2, 1 equals 1, and 2, 3, because a nums 2, nums 3 equals 2, 1 equals 1. Adding up these pairs, we find that the total count is 4. Now, let's examine another example where nums equals 1, 3, and k equals 3. In this case, we are looking for pairs where the absolute difference equals 3. However, there are no such pairs in this input because the only possible pair, 0, 1, gives a nums 0, nums 1 equals 1, 3 equals 2, which does not match k equals 3. Therefore, the output is 0. Next, consider the input nums equals 3, 2, 1, 5, 4, and k equals 2. For the array nums equals 3, 2, 1, 5, 4, with k equals 2, we need to find pairs where the absolute difference between the elements is 2. The valid pairs are 0, 2, because a nums 0, nums 2 equals 3, 1 equals 2, 1, 4, because a nums 1, nums 4 equals 2, 4 equals 2, and 3, 4, because a nums 3, nums 4 equals 5, 3 equals 2. This gives us a total of 3 pairs. With this understanding, let's discuss some important constraints and edge cases to consider when solving this problem. There are a few edge cases to keep in mind. If the array nums has only one element, the output is always 0 since no pairs can be formed. If k is 0, the problem reduces to counting pairs of identical elements in the array. On the other hand, if all elements in nums are distinct and k is greater than the maximum difference between any two elements, the output will also be 0. Finally, when k equals 99, the largest possible value, the task becomes finding pairs with the maximum difference between elements in the array. These scenarios help clarify the behavior of the solution under various conditions. To solve the problem of counting pairs with an absolute difference of k, we first consider the brute force approach. This method is straightforward and involves iterating through all possible pairs in the array using two nested loops. For each pair, we calculate the absolute difference between the two numbers and check if it equals k. If it does, we increment the count. This approach has a time complexity of n squared, because we are evaluating every possible pair in the array, making it inefficient for larger inputs. On the other hand, it has a space complexity of 1, as it doesn't require any additional data structures. However, the quadratic nature of this method makes it impractical for situations where the array size is large, which is why we consider a more efficient alternative using a hash map. To address the inefficiency of the brute force approach, we use an optimized method that leverages a hash map for efficient pair counting. Here's how it works: we initialize a hash map to keep track of the frequency of numbers as we iterate through the array. For each number in the array, we calculate its two complements, namely number plus k and number k. These complements represent the values that, when paired with the current number, would result in an absolute difference of k. We then check the hash map to see how many times these complements have appeared so far. The frequency of these complements contributes directly to the count of valid pairs. After updating the count, we add the current number to the hash map and update its frequency. This method is highly efficient with a time complexity of O(n), as it processes the array in a single pass, and hash map operations like lookup and update are O(1) on average. The space complexity is O(n) due to the hash map, which stores up to n elements. By reducing the problem to a series of hash map lookups, we avoid the need for nested loops, making this approach significantly faster. Among the approaches considered, the optimized hash map strategy is the clear choice due to its efficiency and scalability. While the brute force method is simple and easy to implement, its O(n)² complexity makes it unsuitable for large datasets. The hash map approach, on the other hand, reduces the problem to a linear time solution by replacing explicit pair checking with complement lookups. The key insight here is recognizing that finding pairs with a given absolute difference can be reformulated as a problem of checking for complements in a hash map. This not only eliminates the need for nested loops but also ensures that the solution remains performant even for larger arrays. Comparing the two approaches, the brute force method is more intuitive but computationally expensive, while the hash map approach strikes a balance between clarity and performance, requiring additional space but significantly reducing execution time. Considering the problem constraints and the need for efficiency, the hash map approach is the most practical and effective solution, making it the preferred strategy for this problem. In this problem, we are tasked with finding the number of pairs in an array where the absolute difference between the elements equals a given value k. Specifically, for a pair of indices I and j, we need to ensure that I is less than j, and the absolute difference between the numbers at these indices is exactly k. To solve this efficiently, we will use an optimized approach involving a hash map. This method avoids the inefficiency of checking all possible pairs, as is done in a brute force approach. Instead, we simplify the problem by maintaining a frequency count of elements as we iterate through the array. To start, we initialize two things: a variable, count, to store our result, and an empty hash map, frequency, to keep track of how many times each number appears as we process the array. The next step is to iterate through the array and process each number one at a time. For the current number, we calculate two target values that could form a valid pair with it. The first target is number k, and the second target is number plus k. These represent the two numbers that, when subtracted from or added to number, would result in an absolute difference of k. We then check if either of these targets already exists in our hash map. If target 1 exists, it means we have previously seen this value in the array, and each occurrence of target 1 forms a valid pair with the current number. So, we add the frequency of target 1 to our count. Similarly, if target 2 exists in the hash map, we add its frequency to the count as well. Finally, we update the frequency of the current number in the hash map by incrementing its count. This ensures that future numbers can correctly identify number as a potential target. The efficiency of this algorithm lies in a few key insights. First, the use of a hash map allows us to track frequencies in constant time, transforming the problem from a nested pairwise comparison to a single traversal of the array. Second, the symmetry of the absolute difference condition is leveraged by considering both number k and number plus k, ensuring we account for all valid pairs. Additionally, we avoid double counting pairs because we only check against numbers that have already been processed. This inherently respects the condition that I must be less than j. In terms of data structures, the hash map stores the frequency of elements encountered so far, enabling quick lookups, while a simple integer variable accumulates the total count of valid pairs. Together, these structures allow us to achieve a time complexity of O(n), which is far more scalable than the O(n)² brute force approach. When implementing this algorithm, it's important to consider edge cases to ensure the solution is robust. For example, if all elements in the array are the same and k is 0, the algorithm should correctly count the pairs that meet the criteria. On the other hand, if no pairs satisfy the condition, such as when k is too large, the count should remain 0. Another edge case to consider is an empty array, where the result should obviously be 0 since there are no elements to form pairs. Finally, the problem guarantees that k is non-negative, so we do not need to handle negative values of k. By accounting for these scenarios, we ensure the algorithm behaves correctly under all valid inputs. Let's analyze the time and space complexity of this solution. The time complexity is O(n), as we only iterate through the array once, and each operation with the hash map, such as insertion or lookup, is O(1) on average. The space complexity is also O(n), as we store the frequency of each unique element in the hash map. To better understand how the algorithm works, consider an example where nums is 1, 2, 3, 4, and k is 1. We start with count set to 0 and an empty hash map. As we process each number, we calculate the targets, check their presence in the hash map, and update the count and hash map accordingly. Continuing the example, when we process the first number, 1, the targets are 0 and 2. Since neither target is in the hash map, the count remains 0, and we update the hash map to 1, 1. Next, for 2, the targets are 1 and 3. The target 1 is in the hash map, so we add its frequency, 1, to the count, making it 1. We then update the hash map to 1, 1, 2, 1. For 3, the targets are 2 and 4. The target 2 is in the hash map, so we increment the count to 2 and update the hash map to 1, 1, 2, 1, 3, 1. Finally, for 4, the targets are 3 and 5. The target 3 is in the hash map, so we add 1 to the count, resulting in a final count of 3. This matches the expected result and demonstrates how the algorithm efficiently finds all valid pairs. This implementation of LeetCode problem number 2006, count number of pairs with absolute difference k, uses an optimized approach leveraging a hash map to count the frequency of numbers as we iterate through the array. The function countKDifference is part of the solution class, which is the standard LeetCode template. First, we initialize two variables, count, which will store the total number of valid pairs, and frequency, a hash map that keeps track of the frequency of numbers encountered so far. The hash map is crucial for efficiently checking if numbers that can form valid pairs with the current number exist in the array. As we iterate through each number in the array nums, we calculate the two possible values that could satisfy the condition nums j equals k. These values are number k and number plus k. For each of these values, we check the hash map frequency to see if they exist. If they do, we add their frequency to the count, as each occurrence represents a valid pair. After updating the count, we update the frequency map by incrementing the count of the current number. This ensures that the hash map remains up to date for subsequent calculations. The algorithm is efficient with a time complexity of O(n), where n is the length of the array nums. This efficiency is achieved because we only traverse the array once and use the hash map for constant time lookups and updates. This makes the solution highly scalable for large input sizes. The space complexity is O(n) as well, due to the storage required for the hash map. Overall, this implementation is concise, efficient, and handles all edge cases, including arrays with duplicate numbers and varying values of k. This is the Java implementation of LeetCode problem number 2006, count number of pairs with absolute difference k. The logic mirrors the provided Python solution, with adaptations for Java syntax and collections. We use a hash map to store frequencies of numbers and calculate the count of valid pairs during the traversal. Java-specific features like map and getOrDefault are used to handle frequency updates and lookups efficiently. To solve this problem, we need to count the number of pairs in the array where the absolute difference between the two numbers is equal to k. For example, in the array 1, 2, 2, 1, with k equal to 1, we will initialize two variables, count, which starts at 0 to keep track of the number of valid pairs, and frequency, an empty dictionary that will store how many times each number has been encountered as we iterate. Starting with the first number, 1, we check if there are any values in frequency such that subtracting or adding k to 1 gives us a match. Since frequency is empty, no matches are found, and the count remains 0. We then add 1 to the frequency dictionary. Moving to the second number, 2, we find that subtracting k from 2 gives us 1, which is already in frequency. This means we've found one valid pair, so we increment count to 1. We then add 2 to frequency. At this point, frequency contains 1, 1, 2, 1. When we encounter the next number, which is another 2, we again check if subtracting k gives us a match in frequency. Since 2 minus 1 equals 1 and 1 is in frequency, we add 1 to our count, bringing it to 2. Adding k to 2 does not yield a match, so no further increment happens. We then update frequency to reflect that 2 has been seen twice, updating it to 1, 1, 2, 2. Finally, considering the last number, 1, we check if subtracting k from 1 gives us a match. It does not. However, adding k to 1 gives us 2, which is in frequency with a count of 2. This means we add 2 to our count, bringing the total to 4. Updating frequency to include another occurrence of 1, we end with frequency as 1, 2, 2, 2. The final count is 4 valid pairs. Now, let's consider a second example with the array 1, 3, and k equal to 3. Again, we initialize count to 0 and frequency as an empty dictionary. With the first number, 1, we check if subtracting or adding k gives us any matches in frequency. Since frequency is empty, no matches are found, and count remains 0. We then add 1 to frequency, so it becomes 1, 1. Moving to the second number, 3, we again check if subtracting or adding k results in a match. Subtracting 3 gives us 0, and adding 3 gives us 6, neither of which are in frequency. So, no valid pairs are found, and count remains 0. Finally, we add 3 to frequency, updating it to 1, 1, 3, 1. Since no valid pairs were found in this example, the final output is 0. In our third example, we use the array 3, 2, 1, 5, 4 with k equal to 2. Starting with count at 0 and frequency as an empty dictionary, we begin iterating. For the first number, 3, we check if subtracting or adding k provides a match in frequency. Neither 1 nor 5 is present, so no increment happens. We then add 3 to frequency, making it 3, 1. Next, with the second number, 2, neither subtracting nor adding k gives a match in frequency, so count remains 0. We update frequency to include 2, resulting in 3, 1, 2, 1. For the third number, 1, subtracting k results in -1, which is not in frequency, but adding k results in 3, which is in frequency with a count of 1. This means we increment count to 1. Adding 1 to frequency, it becomes 3, 1, 2, 1, 1, 1. Continuing with the fourth number, 5, we check if subtracting or adding k gives a match. Subtracting k results in 3, which is in frequency with a count of 1, so we increase count to 2. Adding k results in 7, which is not in frequency. We then add 5 to frequency, updating it to 3, 1, 2, 1, 1, 1, 5, 1. Finally, for the fifth number, 4, subtracting k results in 2, which is in frequency with a count of 1, so we increment count to 3. Adding k results in 6, which is not in frequency. Updating frequency to include 4, it becomes 3, 1, 2, 1, 1, 1, 5, 1, 4, 1. At the end of this iteration, we determine that the total number of valid pairs is 3, which is our final output. To analyze the time complexity of the solution, we begin by focusing on the main iteration through the nums array. The algorithm processes each element exactly once, performing a constant number of operations per element. Specifically, for each number, it performs 2 dictionary lookups to compute the contributions of number k and number plus k to the count. These lookups are O(1) on average due to the efficiency of Python's hash table implementation. Additionally, the frequency map is updated in constant time using a dictionary assignment operation. Since the loop runs for all n elements in the array and each iteration involves only O(1) operations, the overall time complexity is O(n). This holds true across best, average, and worst cases because the algorithm structure doesn't change based on input characteristics. It always processes every element exactly once with O(1) operations per step. Now, turning to space complexity, the primary factor is the frequency dictionary, which tracks the frequency of elements encountered so far. In the best-case scenario, such as when all elements in nums are identical, the dictionary contains only one entry, resulting in O(1) space usage. On the other hand, in the worst case, where all elements are unique, the dictionary grows to store n entries, leading to O(n) space complexity. Apart from the dictionary, the algorithm uses a constant amount of additional space for variables like count and the loop variable number, which contributes O(1). Therefore, the total space complexity can be expressed as O(n) for the frequency dictionary plus O(1) for auxiliary variables, making the overall space complexity O(n) in the average and worst cases. Let's compare this optimized approach to the brute force method. A naive brute force solution would involve iterating over all possible pairs, I, j, in the array and checking if the absolute difference between nums, I, and nums, j, equals k. This requires two nested loops, where the outer loop runs n times and the inner loop runs up to n1 times, resulting in a time complexity of n squared. The space complexity in this case is 1, since no additional data structures are used. In contrast, the optimized approach eliminates the need for nested loops by leveraging a frequency dictionary, reducing the time complexity to n. The trade-off is an n space requirement for the dictionary, but this is a reasonable compromise given the significant reduction in time complexity. Mathematically, the optimized solution's linear time complexity arises from the single traversal of the nums array, combined with the constant time operations for dictionary lookups and updates. The space complexity remains linear, driven by the number of unique elements in the array. This makes the optimized solution far more efficient and scalable compared to the brute force approach, particularly for large inputs. When solving this problem, there are a few common mistakes to watch out for. First, some people forget to take the absolute value when checking the difference between two numbers. The absolute difference means we need to consider both positive and negative results, so if you skip the absolute value, you'll miss valid pairs. Another frequent error is counting the same pair twice, once as I, j, and again as j, I. The problem explicitly requires that I be less than j, so each pair should be counted only once. Lastly, relying on a brute force approach with nested loops can lead to inefficiencies. While it may work for small inputs, when the array becomes large, approaching 10,000 elements, this method often exceeds the time limit. Optimizing your algorithm to avoid these pitfalls is crucial for success. Another area where mistakes occur is in handling edge cases. For instance, when k equals 0, the condition simplifies to finding identical numbers in the array. If you don't account for this specific scenario, your solution may overlook valid pairs. Additionally, using a frequency map can optimize the solution, but it's easy to make errors when updating or initializing the map. For example, if you forget to update the frequency correctly, your program might either count too many pairs or miss some entirely. These kinds of oversights can significantly impact your results, so paying close attention to edge cases and the proper use of data structures is essential. Now, let's take a look at some insights that are particularly useful for interviews. This problem is a great opportunity to showcase pattern recognition skills, as it involves identifying absolute differences, a concept that appears in many other challenges, such as checking for specific sums or mathematical relationships. Interviewers also want to see if you can move beyond brute force solutions and consider spacetime trade-offs. For example, using a hash map to achieve an n solution demonstrates both efficiency and practical problem solving. Additionally, discussing edge cases, like when k equals 0, dealing with empty arrays, or handling arrays with identical values, shows your attention to detail. Finally, scalability is often a discussion point. Explaining how your approach handles large inputs, and why an optimized solution is preferable to n squared, can make a strong impression. This problem also connects to other common challenges, which makes it an excellent stepping stone for practicing related problems. For example, in the classic two-sum problem, you find two numbers that add up to a target, and hash maps are often used to optimize the search. Similarly, three-sum extends this logic to triplets, often requiring sorting and two-pointer techniques. For sum 2 pushes this further by counting combinations of sums across 4 arrays, relying heavily on hash maps for efficiency. Finally, k-diff pairs in an array is directly related, as it also involves counting pairs with specific differences, but may include additional constraints. Exploring these problems can deepen your understanding of pair-finding strategies and their variations. To solve this problem, there are 3 main approaches you can consider. The first is the brute force method, where you use nested loops to check all possible pairs, I, j, and verify if their absolute difference equals k. While easy to implement, this approach has a time complexity of n squared, making it inefficient for large inputs. A more optimized solution involves using a hash map or frequency count. Here, you store the frequency of each number and check if the numbers x plus k or x, k exist in the map. This approach has a time complexity of n, and requires additional space but is significantly faster. Lastly, you can use the sorting plus two-pointer technique. By sorting the array first and then using two pointers to find valid pairs, you achieve n log n, time complexity and 1 space. While this method is more space efficient than hash maps, it can be slower due to the sorting step, especially for unsorted input. Each approach has its trade-offs, so choose based on the problem constraints and requirements. Great job! In this session, we tackled an interesting problem and explored its solution. Remember the importance of optimizing for time and space complexity. Keep practicing, and feel free to like, share, and subscribe for more content like this. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!